All right, everybody. I think we're all back and set up and ready to go in the room. So we're gonna keep marching forward with this next section. Hopefully, this break was a good chance to get lunch according to your appropriate time zone and take a breather. And let's dive back in. So in the material, we've got 4 major presentations. It looks like we're going to try and get at least the first 3 of this day 1 done. So we just finished that last section that is the vector functions training. So we've now hopefully built up a familiarity with what these ASSET vector function type systems are, how they're used, and you've been exposed to that. Now we're going to go one step further and say, demonstrate that using these vector functions, you can construct ODEs to define solution spaces in ASSET. And then those ODEs are your interface point for a lot of other ASSET functionality like integrating, which we'll cover now, and optimization. So this is the ODEs and integrator section. So ASSET has the option to enable optimal control problem and integrators on any ordinary differential equation, so ODEs. So in ASSET, what an ODE is it's a special type of vector function that takes a specified form. So an ASSET ODE uses these new argument, these ODE args. So in your previous examples, we just had ASSET arguments. Vector function arguments was our only interface. ODEs are still using that argument type system, but it allocates them in a special way. So in ASSET ODE, which you would define for your solution space, like the 2-body problem or CR3BP, you'll define those as an ODE. It's going to expect states in a very special configuration. It's going to first form a function where your first arguments are your states. So whatever size it is, commonly in astrodynamics, you'll obviously have 3 position, 3 velocity. So index 0, 1, 2 is position, 3, 4, 5 is velocity. Then, however many states you have, at the end of your states will be appended time. This is a new addition to your ODEs. Even an autonomous system like the 2-body problem, where time is not actually an input to determine the next step, even in those, a time variable gets appended automatically to an ODE so that you can track motion and propagation through an ODE. So you've got states, however long your states are. Next, a time variable gets appended. After that are optional calls. So the first optional call is a control variable. So maybe you have a prograde engine, so there's a 1-dimension sized control, and that's just how much your prograde engine throttles up and down. And maybe you have a higher order. Maybe you have a thrust direction and magnitude. So you've got a vector, a size 3 control vector that is the actual acceleration vector being applied to the vehicle. So whatever size your controls are defined as, those get appended into your ODE after time. Then finally, there's a parameter, an ODE parameter input that is an option to be put in of course, its dimensionality, whatever its dimensionality is. ODE params are kind of a special case. We don't really touch on them in this training, and it's honestly almost hard to even think of use cases that need them. One example, if you read through James's dissertation, or if you look through the ASSET docs, one example of using an ODE parameter is something like, excuse me, something like, say you have a cannon with a fixed amount of powder, so you're putting the same impulse in, and you want to optimize the cannonball diameter to optimize some objective function. You could set that diameter to dynamically compute relative to the parameter. But for the most part, it's mostly important to remember, excuse me, ODEs will have states, time, then control. Okay, sorry about that. So we've used vector function arguments previously, like this import that you see on this. So to write a generic vector function, you use vector function arguments. If you are specifically defining a solution space, so you need an ODE model, you will use this new special type called ODE arguments from the optimal control library. So args comes from vector functions, ODE args comes from optimal control. Essentially what it is you are still allocating space for some sized vector function. So in this example up here, you can even see we're going to produce this XTU, so states time control. This is still an ASSET vector function, but it's specifically of the form of however many state variables you have, how many U variables you have, controls, and params. So this XTU, we're not using vector function args, we're using the optimal controls ODE arguments. It's getting passed in 6 states, 3 controls. So this is a size 9 vector function. So that size 9 vector function, you will likely and very often want to partition apart into your states, your time, and control. So there are convenience functions added to this special type for isolating those. So in args, you would run head 3 to get states, let's say. If you only have 3 states, you can also do this instantiated args as xvect, tvar, or uvect to pull out all of your states, all of your time index, or all of your controls. So it is equivalent inputs. You still have the methods of head, tail, and segment. It's just now, because this is a special type, it has these added methods for isolating either a type of the inputs or an individual index. So for example, over here, if we want the state vectors, we could just take this whole XTU thing, which is, again, not a vector function, it's an ODE arg. Sorry, it is a vector function type. We're not instantiating it from the vector function args. It's instantiated from optimal control ODE arguments. So you could absolutely just pull the head 6 of this to get the states, or the equivalent statement xtu.xvect will just return all of the variables of your states. Same thing for U and time. Once you've allocated these or separated these, again, it's just like with vector functions. It inherits a vector function type and those associated methods. So you could take this xvect term that we broke apart, and it still has the list method to pull out all the scalars, or you could do xvect dot head 3 if you wanted just position. So
question?
Attributes for the X bar, Y bar, or U bars, that it's keeping the size.
Hang on just 1 second online. Sorry, we had a question in the room.
Lengths of each one of those variables, I guess, saved in the class that we are. So
yes.
when you pull X back, it knows how big they are.
Yes. So the question was, when you're using this ODE args way to instantiate, do these member variables know the proper size that you've input? And yes, this vector function that results, because it's been appended xvect or uvect, it will dynamically know, hey, I was instantiated with, in this case, 6 state variables. So running .xvect will give you the equivalent of head 3 or head 6. Yeah. And then there was a question online.
Yeah, I was wondering about the OC.ODE arguments. Why did you use that instead of ODE args, like the bottom line import? Could that be used also, or is it different?
Absolutely. So yeah, here we are typing it out in the most verbose way to show it's underlined, but similarly, in that previous example, we went from the vector function library and imported arguments as args. For implementing this, it's pretty common to import ODE arguments as just ODE args.
Okay, just checking if there was anything different. Okay, thanks.
Yeah, definitely. That's a great question. Thank you. So yeah, this is just the verbose way to type it, but in the future, I think we even might list ODE args as that shorthand, just how args is a shorthand import name for arguments. Yeah. Any other questions in the room or online? Cool. I think the big thing to take away is these ODE args are coming from the optimal control library, not from the vector functions, but it's producing a special instantiation or a special type of vector function args that have states and controls, and those will get used right now. So using why would we use these ODE args instead of vector function arguments? Vector functions, if you can recall, we wrote some just convenience functions in vector function format in those last examples. So we had things like calculate the angle between. Something in that vector function language or written as just a vector function is perfectly sufficient and is all you need to add as an objective function or a constraint to an optimal control problem. But for the dynamics, because we have to, in optimization, we have to somehow transcribe the dynamics of your solution space. You know, are you using the two-body problem, the CR3BP and ephemeris model? These ODE args are used to instantiate ASSET models, ODE models that can represent the solution space you're in. So that's why we specifically call out states versus controls versus ODE params, because when we move on to optimizing problems, states are going to be on the back end automatically constrained to obey the equations of motion that you define, and controls will be exposed to the user as something that can influence those states. So that's why we have this special type system. So using this special type system, we are going to now also use the base class that comes with the optimal control library called ODE base. So if you're familiar with using object-oriented programming in Python or any language, you can have a class that extends a larger base class. That is all of the ODEs that you write. Any problem space, solution space that you want to transcribe in ASSET will be an extension of this ODE base class. So we recommend, or the way to interface with this is to write a class in Python structure. So you do a class, you call class, you give it your class name, and you instantiate and say, hey, this is going to inherit from the ODE base class from ASSET's optimal control library. So once you've done that, you need to, for any class, you need to define an init function, which is essentially just a constructor of when I instantiate this two-body ODE class, how do I construct it? It'll automatically run init. So init gets self. This is just standard object-oriented programming. And you can then also pass any Python constants that you need into the init function. So in this case, we're going to use mu for the gravitational param as a constant that gets passed into the ODE. So then within your init function, you're going to use these ODE args to build a structure, a vector function structure of that special type. So in this case, it's ballistic propagation. So there's 6 states, position and velocity, no controls, and no parameter. So we're going to allocate. Notice this is not just x. In all of our previous examples, we did x is equal to args 6. This is now xt is equal to ODE args x variables, because when you call ODE arguments, it's going to automatically append the time variable at the end of your states. So these 3 lines are equivalent statements, just showing you can write it out in a verbose manner and declare any of your empty inputs. But if you're not using ODE params and if you're not using control variables, you are absolutely able to just pass in the relevant one. So if it's a ballistic propagation, just pass in the number of state variables that you're expecting.
So where does the time variable live? Is that a parameter in the ODE based class? How would we pull the time?
Yes. So as soon as you allocate a target from your ODE arguments, it's adding time to it. So in this example, we have 6 states. So this XT is actually size 7 because it's been past the 6 states and it's going to get time appended to the end.
Okay, I understand. So it's extending X bars with another parameter called time, and XT is of dimension 7. Got it.
Yep, absolutely. And then we'll have future examples where we're appending controls in. So recall it's always going to use this same format where it'll do state. ODE args is going to return to you states, one vector function that's states, time, and then any controls and parameters you have. So if this example, if we had 3 control variables, so we call this line, we would then probably want to call this XTU. But of course, it's just a variable. You can name it whatever you would like to name it. So this would then be ODE args of 6 and 3 if we had 3 control variables, which would make this size 10. So the first 6 indices would be states. The 7th index 6 then would be time that gets appended in, and then the last 3 would be control. So we're going to get some more exposure to that. Yeah.
Okay, so you're saying that the time is implicit. Can you explicitly state it in that as you've written it out?
So you're asking, like, can time be an input to ODE args?
Yeah.
It cannot. So ODE arguments only can handle number of states, control, and ODE params. It will automatically create and give you a time.
And the time goes between X bar
and time is always appended between X bar and U bar. So that is definitely something to keep in mind, is the time index is inherently now going to be dependent on the size of states. So if you have, say, one ODE that's just the 2-body model, so you've got 6 states, time is going to be, XT index 6. But if you then create a separate one that's a 2-body with mass, and you create mass as a state variable, now states are size 7. So index 6 is now your mass, and time will have been allocated to index 7 now. So keep it straight, or have a reference like in this, where you're allocating your sizes so that you know where your values are in this large structure. But there's also these convenience functions to just break apart and get states of whatever the size they are, get time wherever it's at, using that .x bars and .t bar.
The only example.
So the question was, is there any way to integrate time as the equation of motion? Yes. So as we construct this ODE, time will, on the back end, time will be handled and integrated forward.
But I mean, like, you have like a separate variable this time.
Yes. Yes.
Can you just kind of say it goes in?
Yeah, so time, you can use time. If you needed time in here, say you have, some problem that you're constraining where velocity is also going to be multiplied by something as a function of time, you can still pull out of this XT term time and do any data manipulation you need with time. Multiply time against something, pass time into a lookup table. Okay. One other question.
Really on the user to have a map.
Yes, yeah, you need
Pick it wherever you want.
Yes, yeah, you need to know what size what size of states and or controls are being passed in, plus your time. So know your indexing. If you're going to use the conventional indexing like head, tail, and segment, know where those indices are based on the XTU format. Or if you're stressed about that, or you're like me and you fat finger things or just make a mistake, using these new member variable or member methods of just explicitly saying, give me my state vectors or give me my control is another way to help manage allocation of how you're going to use those subcomponents.
Now it's just stuck in there.
Yes. So the comment in the room is, a lot of times if you use SciPy integrators or MATLAB, time is something that you're handling in this. In these ODE, when you define an ODE, really all it's expecting is it needs to know how many states and controls it has, or params, but I'm going to kind of leave those off since they're not really in the scope of this training. So it needs to know how many states and controls you have, and it just needs you to compute what are the time derivatives, the continuous analytical time derivatives of your states that are being passed in. So you'll notice the output, what we conclude. I'm getting a little ahead of myself. So once we've allocated states and controls, it will append time to that structure, that vector function structure. So in this case, this is size 7 because we've got 6 states and time automatically gets appended. We are then free to break those states up however we want. All of the member methods are still applied to this. So everything you use to partition and break apart vector functions, you can do to partition and break apart these ODE args into whatever relevant components you need to calculate the derivatives of your states. So once you finally got some VF stack, so a size of stack that has the same size as your your state variables, you're now going to do the super init. So you're essentially now running the initialization method of this ODE base class, passing in the derivatives as a vector function. So this VF stack makes a size 6 vector function, the derivatives, and then the size of your states, size of controls, and parameters as relevant. So this is how any ODE that you need to construct, any problem or solution space that you need to integrate in or optimize in, you need to transcribe the mathematical dynamics of that problem based on what are the states of that problem, based on how you've derived it. Do you have any external controls that are being applied? You can now create an ODE args of that, break it apart into its appropriate components, and then initialize your base class using the derivatives and then allocating the size of what's the size of your states and what's the size of controls. So we're now going to move into a simple example. So let's just talk through the code of this example here. And then I believe after that, we've got a practice. So we've got a 2-body model with a size 3 control vector. So remember in the last exercise, we wrote that function. We just used vector functions. We didn't use ODE args, but we used functions to essentially compute a 3-body or a 2-body problem with some engine with acceleration alpha, and a U vector got passed in as a state at that point in time, and we had to append it to the RTN frame. Here, we're just going to write, give me a 2-body low thrust ODE. I want the 2-body gravitational acceleration and a size 3 control vector that is essentially gets multiplied by alpha as a scale for a thrust scale and gets pointed in whatever U vector direction is. So again, Any ODE, you're going to start as a Python class of some name and use its base class as ODE base. You're going to define the init function and pass in any constants you need. So in this case, we need the gravitational acceleration and we need the engine acceleration. Now here, instead of like in your previous example where we did a vector function args size 9, here we're going to go 6 states, 3 variables, and instantiate. This is now a size 10 special vector function that use the ODE arguments, knowing that it has 6 states and 3 controls. So this structure right here is a special type of ASSET vector function. And it had the first 6 indices are states, index 7 is time, and the last 3 indices are control. So we can now let's break this apart. Our 6 states, we want to get our 6 states. So we can do this xtu structure .xvect to get all of the states. And we still have access to this toList function, and we pass in start at index 0 and give me size 3, start at index 3 and give me size 3. So we are breaking this large size 10 structure into position and velocity. These still are not data storage yet. These are vector functions. So everything you learned in that last section and all the getting used to vector functions, these are still vector functions. Then we do something similar with control. So this is essentially the engine throttle. So now we can compute G exactly how we did previously with 2-body. It's minus mu, R normalized power 3. Ta-da, you have ballistic 2-body motion, but your acceleration in this low thrust problem is your size 3 acceleration due to the planet plus the control vector scaled by the scalar alpha. So now you've got acceleration. We know that r dot is just velocity, v dot is acceleration. So we can compute some variable name. Standard practice, we just call it ODE because this is the derivatives of your states, but you could name this whatever you want. ODE, we're now just going to stack r dot and v dot. So we now have this ODE is a size 6, so it corresponds to our state vectors. It is a size 6 vector function where each element is the derivative, the time derivative of the inputs. So that kind of logic should be consistent with whatever numerical integrator you use, NumPy or SciPy, MATLAB. You need to define what's the time derivative of this ODE. Then we're going to use the super init. So we're essentially calling the init function on this ODE base, passing in the derivatives vector function, and then allocating again the size of states, the size of control. So, giving this time to have been walked through, hopefully it's feeling a little more familiar. Let's move on to a practice. So this is why I said use a script and save the practices from part 1. When you have those, it makes these practices a lot easier to do. So turn those equations, CR3BP equations of motion that you wrote in part 1. Right now, you have it just as a vector function that you instantiate in Python. Try to use the ODE args that we just introduced to turn the CR3BP problem into an OCP or a ODE instead of just a vector function. So because I don't know if the slides have gotten emailed out yet to everyone, we're trying to work that in the background. So I don't know if the slides have been emailed out. Because you should already have the equations of motion from your previous statement, I'm actually going to pull up on this and leave on the screen this other example to show the syntax of ODEs. They have been sent out. Okay, perfect. So we'll take a few minutes to do this practice problem.
There's no like control vector you want in this practice problem, right?
Oh, correct. Good point. So for this case, let's do no controls and no ODE param. So it's just ballistic propagation in the CR3BP. So just the state vectors. And anyone online doing this exercise also definitely chime in if you feel like you're stuck or not sure how to start the problem or run into bugs. We want this to be as interactive as it can to help kind of live debug. So we got a comment in the room I'd like to clarify. I realized to previous example, we didn't have these transpose symbols. You can essentially ignore these because ASSET, if you have a one-dimensional vector function and multiply it to a matrix, it gets treated as a column vector, but you don't need to do the transpose as a user on your side to treat it as a column vector. So I'm even gonna slash these transposes out. Whatever you had in your vector functions test problem is the identical implementation. So sorry about any confusion there. Okay, hearing nothing, how about we keep marching on? So we'll move on to the next slide. So let's walk through the example on how we had done this. So again, as we've shown in all of these, you're going to start with a Python class of the appropriate name, and its base class is going to be this ODE base. We define the init function for this class. It always, of course, has self because it's object-oriented. And then in this case, we needed to pass in mu. So in your vector functions example, mu was the Python input to the function. Now it's the input to your init function. We are size 6 of just states, so you can do this ODE args. I know we had a question earlier, ODE args versus ODE arguments. We just imported ODE arguments as ODE args in this example, so it's the identical expression, just less verbose here. So states and time with 6 states, so this is a size 7 vector function. We can then pull the head 3 as R for states, and now we can't do tail 3 for velocity, because remember, time is the last index here, so we do segment 3, or segment and start at index 3 and do size 3 to get R and V. And now here we do the exact same. These calculations are identical to what you had in your derivation of this problem with vector functions. So I think I missed even this part. So now that you've allocated it as ODE args, partitioned apart your RV and left T off for the states as vector functions, you can now proceed exactly how you had it written in your previous statement. But now instead of just returning the VF stack like we did in our previous example, we now pass that VF stack of the time derivatives into our base class init function and then allocate size 6 variables. So 6 states. We got a question. We do not go into in this training what the base class is, but we can point to, in a future slide, we'll point to where it lives if you want to look at any of the source. Yeah, that's fair. That's fair. So yeah, we haven't shown what this base class looks like, and we don't quite get into that in the scope of this training, but it is, we do have a section a little later on that will show you where, when you install ASSET, where do all of the components live, including this base class, so that anyone can click through.
Question.
Yeah.
Yeah, the last super statement. Why is it a constant 6, whereas before it was something else, X vars and U vars?
Yes, that's a great question. So here we put in a constant 6. Here we were using X vars. It is totally just a different way to slice the same pie, where here, for kind of a more verbose way to teach it, we kind of broke it apart into X bars is a variable of just size, it's an integer size 6, and then we return size 6. This
Okay.
superclass init function is just expecting your ODE argument or your ODEs and then integer sizes of states controls.
Okay, got it. It's expecting an integer, and before you just made it explicit, called it something.
Yes.
Yeah, got it.
Yes.
All right.
Great catch. Definitely. Yeah, that's a great catch. So you are free to, if you want to just allocate it out as a variable of, my X bars is size 6 and allocate that variable as an integer. Or in this case, how it was written, instead of passing in that X bars, which is again just size 6, we just passed in the integer. So this hopefully demonstrating, is you can instantiate these with as verbose or as compact as you would prefer as a user.
Specify everything out. Just take it as short as possible.
Yeah. So the question was, is it better to specify everything out? And that is computationally, it makes no difference. It is all user preference. Do you like having these sizes as integers stored as variables so that you can just pass the same variables through? Or do you just want to specifically call them out each time you run it? One thing that smooths it over is if you do it as a variable, like we did in this previous example, you now know, hey, X bars is declared to be the integer 6. So when you do ODE args and when you declare it here in your init function, you're handing it the exact same number.
Right.
Personally, I write it without that because I want to test my own, if I'm changing from size 6 to size 7 because I added another state variable like mass, I want to really enforce to myself, hey, Aaron, don't forget you changed the size of states. So instead of using the convenience of it being allocated, I want it to error out on me if I don't remember that, hey, I'm using the size 7 for my ODE args and size 7 in my init function. So it's entirely user preference.
So the ODE base class is flexible enough to accept ODE, comma, number of states, and then optionally, so that's the minimum, right? And then optionally, comma, control variables. Is that right?
Absolutely. Yep, you're entirely right. So just like in ODE args, it like you said, absolute minimum, it needs to know the size of states. And then next is optional inputs of size of controls if you have any, and then ODE params if you have any. But if you're not using params or controls, it's robust enough to handle. If it's given less inputs, it's going to assume, okay, you're just handing me states.
Okay, so what we see here is the minimum, and then you can add 2 more parameters separated by commas.
Yep.
For the first being controls and the second being the p-vars, which you're not covering today.
Yes. Yeah.
Okay.
Sorry. Of the 2 optional, controls and then p-vars. Absolutely. Yep.
Okay.
Yeah, great questions and great points. Yeah, so the minimum is you need to return your derivatives and your size of states, but if it is controlled, if you instantiate it as controlled, make sure to pass the size of controls and then any p-vars if you have any. So let's do, now that we've gotten to kind of walk through, do a practice and then walk through that solution, let's do just one more test with, again, you'll remember our last function that you wrote for the vector function slides where it was a 2-body with a low thrust engine. In that case, we forced it to go in the RTN direction. Here, let's do an example instead where you have 7 states. So you have position, velocity, and mass. So states of size 7 now, and 3 controls. So we're adding controls in, but in this case, we want the controls to be applied in the RTN frame. So in your derivatives that you're returning here, you've got your two-body problem. I think we're pretty familiar with that, plus user inputs of constants of tau and m. Those are both going to be Python inputs, along with G0 and ISP. So this section are all Python inputs. But you want to compute that RTN basis frame or basis vector matrix like we did in a previous example. This time you're going to do matrix operations with the control vector. So let's give some time to try and walk through that example. So remember the important things to remember that are changed from that previous example is now size 7 states because we also have mass. And then we also want control that is in RTN, so we need to convert those. And finally, remember our output, what we're returning needs to be the time derivative of all of our states, right? So this first one, this v vector is size 3 because it's the derivative of your position. This acceleration term is size 3 because it's the derivatives of your velocity. But mass is going to be a state now. So you also need the term that you return, that ODE that you compute, needs to have a time derivative of your mass also, since it's a state. So in this case, we're just going to do the magnitude of your control vector times the tau, G0, and ISP, all of which are your Python inputs, constant inputs to Python. A little bit more complex of an example, but let's take some time to work through this one.
Okay, I had some questions.
Yeah, absolutely.
Yeah, can you tell me the control vector, what that physically represents? Is that a force? What is that?
Yeah. So how we're formatting, you can think of it in this formulation as your direction of an engine and a throttle. So okay. Essentially, U vector in general is an arbitrary control. Excuse me, an arbitrary control that when we get into integrators optimizers, the asset will be able to handle that control vector subject to any constraints we append on it to try and optimize the states and objective function. So in this case, we are saying, let's formulate the problem where the U vector is a vector of essentially the direction and its magnitude of an engine's thrust for like a low thrust engine model. So the magnitude of U is essentially, it's going to return us a scalar. That's going to be the scale of your thrust. So if the engine's fully on, magnitude of U will be 1. And if it's entirely turned off, magnitude of U is 0. But then the direction of U also is where in the Cartesian frame is U pointing. However, the controller, we're trying to formulate this where U is not in this Cartesian frame, it's in the RTN frame. So we have to do an intermediate step where we compute the conversion from RTN to Cartesian, which we had shown before. Now, whatever the optimizer or our control laws we append do to U in the RTN frame will apply as a thrust, because we're doing tau over mass to essentially get an acceleration, will apply as a thrust in the Cartesian frame.
Okay. And then all these examples you're having us do is creating, classes. And I was wondering, will you go over an example of use cases for these classes in Python or somehow?
Yep, absolutely. So these classes, a little sneak preview at what comes later in this section.
Okay.
The reason.
Yep, I understand.
So we're practicing now instantiating these classes, because these classes, this method that we described in these previous examples, come on slides, there we go. Like this, once you have this defined, an ODE model defined, you can instantiate this, and that is now your interface point in ASSET. How do I spawn integrators if you just want to do propagation, and how do I spawn optimization phases? This is we're defining the interface point to be able to spawn off optimal control problems and integrators.
Oh, okay. All right, thanks.
Definitely. So one one tip that came up in the room is, now that your state size is changing in this example, since you are instantiating the ODE args as size 7, if you take that resultant and run that .xvect, it's now going to return you a size 7. It's going to return all of your states. So it will dynamically change the size of the .xvect and .uvect of your ODE args to adapt to whatever size you told it your states and controls are. Okay, so I think we're about wrapped up in the room. So I think we're gonna go to the solution now and kind of walk through how to formulate this one. Okay, so this example, again, I know I mentioned this one slightly changes a little bit more from the vector functions demo that we did. So it's a little bit more user modification compared to the CR3BP example. So hopefully we're taking incremental steps enough to kind of add complexity without feeling like you're entirely shoved in the deep end. So again, as always, we're going to call it a Python class with some name. This is a finite burn RTN model is what it's named here. It inherits that ODE base class as always. Now our init function, we've got a few different constants. We've got mu, the gravitational accel. We've got tau, ISP, and G0 for these engine calculations. So these get passed in as well. We are size 7 x variables. So you can see here also we're using, we've used interchangeably in the examples, either just putting in integers for the sizes into ODE args and the output, or just allocating it as a variable. So xvars is just a variable of integer 7, uvars is size 3. So now xtu becomes the ODE arguments of that many states, 7 states, because we added mass, and controls, since we're using a controlled form. So this xtu is size. We've got 7 states, 3 controls. It is now size 11 because the first 7 elements of xtu are the states. The next element is time. That automatically gets appended in by the ODE args. And then the last 3 are controls. So now we can partition those apart however we like. Again, there's many different ways you can slice this. It's all user preference at this point. So in this case, we took that xtu.xvect, just like the question in the room said. So now xvect here is size 7, not size 6, because we have mass. So then we just did toList and said start at index 0, give me a size 3, so that's position, index 3 for velocity, and then index 6 size 1 for give me the mass scalar. Control, conversely, is just a nice easy to this xtu. We could do xtu.tail3, or we could do xtu and do the Python bracket index search, or we can do this xtu.uvec to get the control vector. Then we, once again, this, we said bonus points in that one previous example. If you just write a separate function that you can instantiate and call to compute the RTN basis vectors. So that's all we're doing here. This is exactly what we had in the previous statement where we get the RTN basis vectors. So this is an instantiated function. We now use the instantiated function with position and velocity to get a size 9 coefficients for the basis vectors. And then we construct those into a transform matrix of column matrix 3, 3. So now acceleration. This is the two-body component like you've been seeing for probably so many times you're tired of me pointing it out now. And then tau divided by mass. Notice mass even dynamically scales. So this will account for your mass decreasing as you use the engine. So tau divided by mass times taking the u vector, which we're assuming, I shouldn't say assuming, we are writing this problem in such a way that we're going to say the u vector that ASSET has control of. In this case, we're going to make the u vector the RTN direction that we're thrusting in. So the u vector gets converted into Cartesian from that RTN to Cartesian matrix we've made. So we can add those together, and now we have a size 3 acceleration. All that's left is we need the time derivative of mass, because that is a state now, so it needs a derivative. So minus tau over g times ISP, very standard. And then we're multiplying it by the norm of our control. So if control is unity, size unity, then we're on full blast using m dot as large. And then as u scales down and becomes a smaller magnitude, you're burning less propellant. So your m dot is smaller. So we've now got r dot, v dot, and m dot. So we stack them all together. This is ODE is a size 7 time derivatives of our 7 states. So once again, we call the super init, pass in our derivatives, the integer size of our states, so 7 in this case, and the integer size of our controls, so 3. We've got a question, yeah. Great question, very good question. So in the room, it was asked, this ODE that we're passing in, this VF stack, do these components that we're stacking together need to be in a certain order? And yes. So just how X states, we're applying some dynamics to X states, the time derivatives also need to correspond. So whatever your X0 is, the first index in this stack needs to be the time derivative of that. So
stack. R dot. It's not.
Yes. Yes, good observation, because this, yeah, the VF stack is unpacking any vectors to get a size, in this case 7. So r dot is actually size 3. So we've got, x, y, z time derivatives, vx, vy, vz time derivatives, and then the scalar m dot time derivative. So since we wrote the problem where the states are position, velocity, mass, it needs position, velocity, mass order of the time derivatives. Yes. Yeah.
There's no convention.
Correct. Yeah. There was a question online, sorry.
Yeah. I'm just trying to better fathom initial conditions. And so, when I set up models, I usually, have a x0 for time 0, the initial state and mass. And so I'm trying to visualize how I would do that here.
Yes. So you don't have initial. We haven't gotten to initial conditions yet.
Okay.
But when you write initial conditions, they will need to also be in the form of these ODE args. So if you've got, for this specific problem, this two-body finite burn RTN, your initial condition will also need to be size 11, and will need to be x naught, y naught, z naught, your velocity knots, mass naught, time 0, and then control vector initial conditions.
Okay, and so we'll get into an example of initial conditions later, is what you're saying?
Yes, very soon. So this is creating a class that we can spawn integrators off of, and then we'll use integrators to propagate out initial conditions very soon.
Okay, all right, thanks.
Yeah, definitely. And then one question that was in the room that I wanted to make sure got said online is, because we are formulating these to just this ODE term that we're passing in is the time derivative of the states in whatever order you want. So we derive it where we've got position, velocity, mass. There is no convention that stops you from doing mass first and then position and velocity, or position, mass, velocity, or if you want it to be wonky just to prove that there's no convention, Rx, Ry, mass, and then the rest of them. You can write it however you want, but make sure that, if you do it in that wonky way where m is between x and z, your time derivatives that you pass forward also need to be x, y, mass, z, and the rest. And then also in the future, when you do integration or optimization, it's also going to return values to you in that order. So it's a good idea to define your state vectors in an organized way that you would actually want to initialize initial conditions in what you want to get time history in. And it's going to be consistent to however you define it in this ODE function. Yes. Oh, good point. Yeah. If we decided we wanted to just say there's no convention regulating it, we're going to do X, Y, mass. You also need to adjust this code to properly allocate it and get, X and Y are going to be your head 2, then segment starting at index 2, size 1 becomes mass. So it's a headache that I wouldn't advise, but you can formulate the problem however you want. You just need to be consistent. Whatever states you allocate these X vars to be in your dynamics, you need to return their derivatives in that same order. And then down the line, your initial conditions, your time histories are all going to stick with that convention. So online, we got a great question that is like beautiful setup for this next stage. So we've gone through all these exercises, writing these classes that we are calling ODE classes. Why did we do that? Why do we spend time doing that and take time even doing examples writing them? It's because in ASSET, ODEs are what expose to us as users. They're what give us a way to interface with the two major components of ASSET, the two main reasons why you'll use ASSET: integrators and phases. So integrators are objects that you can essentially spawn off of an ODE that does propagation. It solves initial value problems. It solves, you can append control laws and do integration. It doesn't have an optimizer in it, but an integrator can do any ballistic propagation you need. The other thing that will spawn off of these ODE classes are phases. Phases are how you interface with ASSET's optimal control problems. So if you need to optimize some problem, or you have states that you need to optimize, you'll spawn a phase off of these ODEs. So as an example, say we wrote a simple two-body class in some of these previous examples. I know we did a more complex one that had a two-body with a low thrust engine, things like that. But say we just had a basic two-body class. You can now instantiate that class, and that instantiation, this ODE object that you just instantiated, this ASSET ODE object, is how you instantiate integrators and then later instantiate phases. So this next section of the training is going to focus on integrators. So we've written the dynamics of our problem in this ODE. So we've gone through, we've done mathematically the time derivative, my states are this, my controls are this size, and my mathematical time derivatives of my states are this. We've defined all of that in this ODE that we've instantiated. Now we want to actually do some problems that propagate solutions that obey those equations of motion. So that's what an integrator is for. An integrator is a utility that you spawn or you instantiate off of the ODEs that we wrote. And they're used for pure propagation. They can be parallelized. And run in parallel if you need to do something like dispersion analysis. They are how you take an initial condition and propagate it for an initial guess, like we were talking about. And also later on, if we're doing collocation optimization, if you want to validate your optimization solution, you can use an integrator to reintegrate your trajectories. So an integrator takes the form of take some initial condition and run it through the equations of motion that this integrator was instantiated from until some time final. So it's going to take the same format, that XTUP format is exactly what your initial conditions are expected to be in. However you allocate your states, time, and controls, that's how you need to instantiate your problem here. So as a practical example with the two-body problem model, we wrote a class, class two-body takes in the ODE base class. We've got all that defined, so we instantiate it. We now have a two-body ODE object. So this is an ASSET ODE object here once we've instantiated those classes that we just wrote. The next thing you do is you instantiate or initialize an integrator object. So an integrator is instantiating it is a method from the instantiated ASSET ODE. So if I want a two-body integrator object, I take my ODE instantiation and say .integrator, and I can pass in a string, which is what integration scheme do you want to use, what algorithm. The default is Dorman Prince 8.7. We also have Dorman Prince 5.4. Maybe you have a use case that you would want that. When making the training material, couldn't think of why you would want to default to 5.4 instead of 8.7, but that's a user option. And then you can define the step size. So once you've done that, you have now initialized and instantiated an integrator object. And remember, there's a lot of kind of inheritance, a pseudo way of thinking of inheritance in ASSET. This integrator is going to obey the equations of motion of the ODE object that it was spawned from. So we wrote how is motion supposed to happen in two-body. We instantiated a two-body ODE, and then when we instantiate an integrator off of two-body ODE, now any initial condition you run through this integrator is going to propagate out from your initial condition to some time final, subject to the equations of motion that you defined in two-body. So often your instantiation will just be this one-line call where you say, hey, here's my ODE that I want an integrator of, .integrator, and pass in some default step size. By default, ASSET uses adaptive step size algorithms with tolerances and constraints, of course. So as long as you have a good initial guess for what a relative step size should be within your ODE, ASSET will do adaptive step for that by default. If you would like, you can also, of course, view what that instantiated step size is, what the min and max step sizes are, and you can set parameters on those step sizes. So once you've instantiated an integrator, say you want to change the minimum or the maximum step size, or you did a test case and don't like this step size that you have or want to do a step size study, you can change those step sizes for this integrator object. I will mention now, and I'll try to mention it a few times, ASSET's default settings, both for integrators and for phases, assumes or they are sized for non-dimensionalized problems. So if for whatever reason you wanted to do an ODE of two-body that was dimensional in meters, computationally, from a computer science standpoint, you probably just should non-dimensionalize, but there's nothing stopping you from doing that in ASSET. It will listen to user input, but when you do that, you'll probably need to change your default integrator step sizes to adapt for the fact that ASSET was defaulted to assume that users are writing non-dimensionalized ODEs and you're running something dimensionalized. So this is the interface to deal with that. All of the examples that we do here you'll notice are non-dimensionalized already. So you don't have to touch the integrator settings in any of these. Similarly, an integrator has defaulted tolerancing. Once again, our defaults are for non-dimensionalized ODEs. So you can do things dimensional, but the tolerancing is certainly going to be way too tight if you're trying to do things in some dimensional ODE. So you can do a dimensional ODE and then write it as changing your integrator tolerances. There's nothing stopping you from doing that, but I would suggest reconsidering non-dimensionalizing your dynamics. So let's look at the basic use. So once you've gone through these steps that I've said ad nauseum, basically at this point of define your ODE, instantiate an asset ODE object, then from that asset ODE, instantiate an integrator with some step size. You now have an ODE integrator object. What you want to actually do with that is take some initial condition, some states and time that are, of course, properly sized to your problem. So size 6 or size 7 states, whatever you define your problem as, and you want to integrate them. You want to run them through the problem. So if you take your integrator object and run just .integrate, it's going to return the final state of your integration. So if you've got something and you just need to know, here's my orbit initial condition in this 2-body model, where's it going to be in 5 non-dimensional time units or 5 days converted into the proper time units, you can just run integrate and run it for 5 days, and it will return the final state. However, we often want time history instead of just a final state. So that is integrate_dense. So you can run integrate dense and input your initial condition and the time final, or there's an optional argument for n, which is how many linearly spaced points do you want your time history to be returned. I will have to look it up. I believe the default size, if you don't specify n, is 1,000 points. But if you need more granularity or less, you can vary this n. It's important to remember when you integrate dense, this n is only impacting the size of a linearly interpolated state that gets returned to you as a user. It does not impact the dynamics. So the dynamics under the hood is doing a variable step size solve for however many, using your defaulted step size and min and max and tolerancing. It's doing whatever it needs under the hood with variable step to satisfy your tolerancing, to step from your initial condition to final. But because your time steps from that may not be monotonically increasing as it goes through less or more stiff parts of your ODE, we return a linearly spaced intermediate steps with this n term. And I reread also and forgot, it doesn't default to 1,000. If you don't pass a variable to n, it returns you the exact intermediate steps, even if those are variable time. So if you want your integration time history to be fixed time steps that are monotonically increasing, go ahead and pass an n term in. So here's an example of doing that, where we take some initial condition that's initialized to 0, but then we instantiate it. This is just a verbose way of creating a size 6 states and size 1 time initial condition, and saying time is 0, let's integrate to time 10. And let's have 100 points in this case versus the exact integration steps in this one.
A question for you.
Sorry, just 1 second. We got a question in the room also, and I'll absolutely come back.
Not taking an nth grid and adding those points inside the solutions. So to those points.
Yes, good point. Yeah. So the clarifier is this difference of integrate dense when you put n. It is Yes, this n is applying your solution that is getting linearly spaced and passed back to you. So I will, yes, it solves the problem, then returns it to you as n. We had a question online too.
Yeah. So you said the default is to use non-dimensional solutions. So, and you have numbers here shown. So if it's R is non-dimensional, how was it non-dimensionalized? Was it reference to like Earth radius or what?
Yes. So how you define the problem will also define what it's non-dimensionalized as. We normally try to instantiate models where your unit length and your unit time are of size 1. So for example, in an Earth problem, we're instantiating the mu value as 1. So the gravitational acceleration is size 1. So from that, we can then work out and apply, let's say, distance 1. I think, one common way is to say, okay, distance 1 is 1 Earth radius, or something along those lines. So now R, if you want something that's 2 Earth radius away, is just R equals 2. And then obviously subject to however you instantiate the mu value. So you kind of need to work backwards if you're doing it non-dimensionalized this way, of working backwards and saying, okay, we want the gravitational acceleration to be 1. If we're doing this problem for Earth, what does that mean for our units? We will also, we probably won't get to it today, but tomorrow we will look at some more use cases of looking at specific systems. There's a good way to kind of standardize the non-dimensionalization process where you can formulate problems with dimensional terms and then multiply it by a scale, a scale factor that dynamically non-dimensionalizes.
Okay, so correct. As far as units, you kind of get to that later. Is that what you're saying? So time in seconds, it doesn't matter at this point because it's non-dimensional.
Correct. Yep.
Or is the solution here? Okay.
Yeah, it will integrate your dynamics in whatever math and in whatever scale you form it as. So in this case, we've formulated it just as, the acceleration term that we're returning in 2-body is mu. So if we pass in a mu value equal to 1 instead of Earth's actual dimensional gravitational acceleration, we now know, okay, an acceleration of 1 is Earth's gravitational accel. So we can then build back up from that. Or we can write structures to help us non-dimensionalize things. So we could say, hey, the acceleration scale is Earth's gravitational acceleration, is equal to Earth's gravitational param. And now anything that we need to scale relative to our problem, any acceleration, we just divide it by Earth's gravitational accel. But that will hopefully make more sense tomorrow when we dive into some more specific Earth and Earth-Moon orbit examples.
Yeah, okay. Because I look at your example here and wonder, if you pick one of these, what is the relation to the others? And that is, you pick, R value of 1, and how do you make a realistic value for V and time and so forth, so you're going to get into that. It sounds like. Okay.
Yep, we'll definitely get into that and give some concrete and some like coded out examples on what we do there. So these are less focused on the actual dynamics and more just the process, but we'll have examples later that are specific, Earth or specific lunar orbits.
Yeah, and then one last question here. I think I understand the first and last, but the intermediate, Can you explain that? How do you
Yes.
set up
You're-
intermediate values?
You're saying this section here?
Yeah. What does that mean?
So because ASSET automatically uses a variable step size integrator, following, if you use the default, it's using a Dorman Prince 8.7 integration scheme. So that the variable step size, as the problem needs, it will adjust the step size. So if you run integrate dense and just give initial conditions and time final, the resulting time history that you're given, time is not necessarily going to be monotonically increasing in equally spaced portions. It's going to return to you the exact integrator output from your variable step size. So this is almost more of a debug, or if you need to study how your integrator is changing behavior, you can run the integrate dense without that. But if you often, if you're going to make plots or show a converged trajectory, you can pass in this number of equally spaced intermediate points.
Okay, so you're inferring that the integrator itself is varying the step size to optimize it somehow?
Yes, so it's not optimizing anything, but we're using a variable step size, Dorman Prince 8.7. So if it has a prediction of, there's definitely further or better resources on the integrator algorithm itself, just looking at Dorman Prince itself. But essentially, if it tries to take a step size that's too large for the gradient, it can reduce that step size to be smaller to make dynamically smaller steps. So say you have a highly elliptical orbit, the parts of your orbit that's near apoapsis, where it's far away from the planet, is pretty smooth, so it's safe to take large steps. But then as you fly through periapsis and your dynamics are changing fast, often a variable time solver will take smaller time steps through those more dynamic regions. So if you do that, if you have an elliptical orbit and you don't put in n, it's going to give you what are the actual steps that the integrator took. Versus for integrate dense, you can just have a linearly spaced grid of where's my state at all of these times.
Okay. All right. Do you have references on these integrators, the DOPRI 8785 and whatever?
Yeah, I can post the name in chat soon, and we'll get references later. There's definitely some extensive references on the Dorman Prince algorithm.
Okay, great. Thanks.
Yep. Okay. So one very important point when using these integrators, emphasis, because it's bolded. I have forgotten this a lot when I first started using ASSET. Time final of your integration is the final time that you're integrating to. It is not a delta time. So if you want to integrate some initial condition for 5 days, if your initial condition starts at time 0 and you say time final is 5, yes, congratulations, you've integrated 5 days worth. You've gone from 0 to 5. But if your initial condition was at time 10 and you say to integrate to 5, the integrator is actually going to integrate backwards in time to get to 5. So you are not putting in a positive or negative time dealt relative to your initial condition time. You are saying, here's my initial condition, including T0, the time that I'm starting with, and you are integrating to whatever time final is. So if time final is before your initial condition, it will back propagate to that time. So keep that in mind, and either the time final that you put in, make sure that it's applying any delta you want, or to be safe, you can say, if you wanted to propagate for 5 time units here, you can have time final is equal to the time index of your initial condition plus 5. because then it will vary and make sure that it changes what the time final is relative to your initial condition. So that's a useful tool for if you need to back propagate or anything like that, or you don't care what the delta time is, you just need to get to this time. But that is a pain point if you forget that this is not a delta that you're applying.
I didn't catch this before. Your time units are days.
Your time units are in whatever you derived your equations of motion to be.
Oh,
So in this case, in this exact case, we wrote everything where acceleration was relative to mu. So if we're passing in mu is equal to 1, then our time is subject to whatever,
Right.
mu relative to the time. So we'll get into handling time and dimensionality a little later. Yeah. So just some basic examples. You can plot, the exact phase here, and it'll show the exact integrator steps, or you can do an interp n and change the grid of if you want to return different state densities at different times or get lens-based. So I'm going to try and move a little bit quicker so that we can try and get everything in. Integrators also have in ASSET, these integrator objects have the ability to do event detection. So event detection is essentially just, I have a function that I want to evaluate, and I either want to record when this function is triggered, or I want to stop integration when it's triggered. So in this example here, say we want some set of different event detections that we want to run, and we want to know whenever a two-body orbit goes through one of the apsides. So we can write a vector function using ODE args, and we can write it. This can be done with ODE args or vector functions. I know that's a little more advanced, but essentially we can have this vector function that's returning our position dot product with velocity. So event detections happen. Event detections are given a function, and the detection happens anytime the function you append crosses 0. So any 0 crossing will trigger that. But you can set the direction that you want. Do you want any apside that we pass through to trigger? You can do direction 0. So now if it goes from less than 0 and passes through 0 to become positive, it'll trigger. And if it goes positive to negative, it'll trigger. Or you can do it one-sided. So if you want it to go, say we want the apoapsis only, you can do direction -1 for this apside function. And that means it's going to trigger when your r.v, as you fly through apoapsis, your r.v is going to go from a positive assessment to a negative scalar assessment. So right at that point, it's going to flag the event. Conversely, the periapsis in this next one is a positive one because it's a 0 crossing that goes from negative to positive. Or you can say direction 0. If you say, hey, whenever this crosses 0, whenever this function evaluation crosses 0, I want to flag regardless of direction. So the final component of setting up an event detection is a stop code. Do you want integration to stop when this happens? Then stop code is true. If you want it to continue on but just flag it, it's false. Or if you have some number of times you want this event to trigger and then it stops, you can put an integer number. So say we take this generic apps function. So it's going to, this function will trigger, it'll be a negative trigger at apoapsis and a positive trigger at periapsis. You could say, I want all apsides. So here's our function. And the direction is 0 because I don't care if it's going positive or negative. And then my stop code, I'm going to set it to 2. As soon as this function is triggered twice, then stop it. So this will fly through a periapsis and an apoapsis and then stop. So once you've constructed this tuple, it's going to be a Python tuple. So you're using paren operators, not brackets, because it's not a list. But you have a tuple that is your function that's being evaluated, that direction, and your stop code, you can pass any number of event tuples into your integrate call, and that will then integrate it subject to those constraints. So you can even pass multiple events. You can make that apoapsis, periapsis, and all apsis events as one big list and run an integrate and see if it flags any of those. Or if you have a stop code on one, obviously if it hits a stop code on any event, it's going to stop integration. So commonly, if you're trying to do a stop code, you will just have one event that you pass in. It still needs to be in a list because the format expects a list of events, even if you just have one. So you can run through. Now notice, instead of just getting a time history, we get a time history and an event locations. So the event locations gets saved off as the first reference, or the first index that you're indexing into is which event from the events you passed in. So do you want the first event, apo is event location 0? Do you want the second event? It's index 1 and 3. And then within that, any event detections that happen, you index again. So say we had in the all apps event detection, we want event number 2, because that's the all apsides event. And then the apoapsis is the first one we pass through, and then the periapsis is the second. So here's an example of that being run, where we've got a periapsis and an apoapsis. It flags when it flies through both of them. And here's that r.v vector function that we're assessing. So we flag the apoapsis for a positive crossing, or sorry, a negative crossing, and then the periapsis for a positive crossing. Correct, because the first one is starting precisely at 0. It's not a 0 crossing there.
So I was going to ask about the same thing, because oftentimes we don't start precisely at double equals 0, right?
Right.
Yes away.
Yes.
So what is the methodology for not, say you want to hit just one event, right?
Yeah.
You want to hit your, go forward one. Oops, again, real quick. So you want to hit your periapsis, but it needs to be after where you're starting, right? So you want one rev, and you're not starting precisely at true and out equals 0 because you defined it that way, right? I mean, sometimes so double precision errors creep in numbers.
Yeah.
So what do you do?
You're specifically asking that first event, correct?
Yeah, right. So sometimes, what I'm trying to do this right now, and ASSET is driving me nuts.
Okay.
So what I'm running into is I start at periapsis, but there's double precision noise in the numbers because I mean integrator and other things can get to that point originally.
Yeah.
Sometimes I'm just before it. Sometimes I'm just after it, but it's within such a small precision of or tolerance of that actual point. I don't actually care, but I can't write code that handles all of the different. It's just a pain in the neck to figure out that this phase works this way and that phase works that way, and sometimes
yes,
you skip it, sometimes you don't.
Yes. So there's two things you can do for that. So the question is essentially machine precision at these crossings. So it is defaulted. It's detecting the crossings. So if you have machine precision here, you can see it's not flagging that first crossing. But say you
Not
now
necessarily machine precision, those tolerance to be integrated.
true. Yes. So, but you're saying, say you've previously done a run and you're going to get really annoyed that its event detection stopped integration a little bit past it if you're inheriting from a previous phase.
Sure.
Well, it can be.
Sure.
Yeah, so
I think I know.
Might count it as a crossing, it might not. All right.
So right. So sometimes you might stop here.
Don't touch the screen.
How about you? Sometimes you might stop there, right? Like within tolerance, but it's random because
Fair.
if you do 10 revs, your integrator tolerances are gonna put you wherever you put you, and small things. I mean, it might not even be. It might not even feel deterministic, right?
Because this is
Right.
actually based on the previous.
Right.
Yeah.
Right, and that one could be based on another one, right? So
Yes. So one thing I would say that may help with that is when you do the event detection, you get two things out, right? You get the time history and you get the event locations. The event locations can be tuned in with tighter tolerance than your integrator if you need.
Sure. All that.
So you can write that in and then base your initial conditions for the next rev based on the event crossing from event locations, not from the time history. Because the event locations should give you exact states right before and right after, I believe you can reference. So you can pull it from event locations.
It just gives you the one.
It gives you the one cross state. Okay. Yeah. Let's work this offline. Yeah. So we'll move on, but when you're at machine precision like that, we'll hone in. The event locations you can, I don't know if you've looked at, you can tighten the tolerance, but you're essentially saying it's going to cross it, but even within that tolerance, it could be on one side or the other of the evaluation function. Okay. Yes, we can definitely look into that. Okay, so here's a plot of a nice deterministic, easy example of clean event detection. But you're right. There are nuances, just like there always are. So one other function that we'll just briefly hit on here, integrators also have parallelism built right into them. So ASSET, if you remember in the first slides, one of our goals was we want this to be an easily parallelizable tool for large trade studies. So the triple pound sign here is any of those previous integrator methods. All of them also have a method _ parallel version, which does parallel propagation of whatever method you call. So integrator.integrateDense _ parallel lets you get time histories of multiple things in parallel propagation. So now you are not inputting an initial condition and a time final. Now you're putting in a list of initial conditions and a list of time finals. And then there's one more input. You need to allocate how many threads you're going to let your computer use for parallel processing. So
is this where Jet?
No, we're not hitting on Jet, but Jet is almost like this version for optimizers.
Oh, okay.
Yeah. One more question.
Something, or you always have this one.
So the question is there a default value for n threads? I think it actually has. I don't think it has a default. I could be wrong. I think it wants you to allocate how many threads you have. So yeah, you know your processor at least well enough from your system info to know how many threads you can afford.
And RAM.
And RAM allocations. So it is definitely a little bit problem dependent. Anytime you're looking at parallelism, there's a little bit more onus on users to make sure you're not over allocating your machine. For shorter durations, 4 to 8, maybe 16 threads is a safe guess. If you don't know your machine, 8's a standard guess at least. Perfect. We've even got thanks very much, Jared. That's a good input so that you can check your machine CPU properties. But yeah, so this is a handy tool for trade space studies or initial guess generation, things like that, where you just want to get results as quick as possible instead of running a bunch of integrators in sequence. There's now parallelism that you can run in parallel. Yeah.
The results that come out of that, are they're time history vectors to the state?
Yes.
What's the organization?
Yes. So the data coming out will be, I believe, I'll double check this and state it a little bit later to make sure. I believe it's going to return a list of time history trajectories with exact steps if you don't pass in n, and with that n. I need to look up if it returns to you exactly the same inputs. If the indices of your resulting trages matches with the initial condition inputs, I believe it does, but I want to double check that instead of definitively saying. But yes. So it will return to this trages term is now a list of time history lists. So it's a list of lists when you've done it in parallel. Okay. So now we're getting into another interesting property of integrators. So all of what we've said is great for if you have ballistic propagation, but we also just did practices where there's a control vector in our ODE. And if you recall, I even said when you instantiate an initial condition, it needs to be the size of your full ODE. So even if you've got ballistic propagation, you need to allocate an initial guess for your control. But because our dynamics don't change the control vector, if you just do a vanilla integrator on a ODE that has control vectors, it's just going to hold controls constant for whatever the controls are in your initial guess. So if you have an engine that you could control, but your initial guess just has it zeroed out, that's fine, but you're not going anywhere in your integration with that engine. You're just going to stay in your orbit. So ASSET has the ability to write control laws as vector functions and append those control laws to an integrator. So you can do something like, in this example, it's a prograde control law times some constant throttle value. So you can take in vector function arguments, just like we did in the first examples, and whatever you return needs to be the size of your controls. So if you have 3 control vectors, your return of this function needs to be size 3. And then at every time step of integration, every integration step, your control vector will be computed to whatever is coming out of this function. So this integrator with control law example here, you again can declare integrator type, or it defaults to Dorman Prince 8.7, so you can just do step size if you want. Then you pass in your control law vector function, but recall these vector functions are using ODE or are using vector function arguments. How do we pass those? It then expects a list of what indices from your state vector, from state time control P, from that, what indices do you want to pass in as arguments to this function that's being called? So in this case, the control law is Dorman Prince 8.7, default step size of 0.1. It uses this vector function for its u vector every time step, which is essentially taking your velocity, turning it into a unit vector and multiplying it by some throttle value, which we've instantiated as 1. And then we need to pass it that velocity component. So we pass it 3, 4, 5 to give it these 3 args. So here's an example of using that no integrator where control's initial guess is 0. You're just going to stay in that elliptical orbit that we were in. And the control is, even though you've got a control vector, it's just zeroed out. And it doesn't do anything to change your states. But with a prograde control law, you can see now you're actually thrusting with that u vector by throttle, and you start getting the spiral out behavior. So this is a good way, even if you want to explore a control law, here's a great way you can actually integrate initial condition states with a control law. Or if you need to do optimization, you can use a control law to at least get some kind of controlled trajectory behavior for your initial guess generation that you'll later pass into an optimizer. Question?
Yeah, X bars.
Yes.
So do you still have a control law that you could apply it this way? Like over
like, can you append this in? I don't believe you can. It's definitely not. If it lets you just append a control law to a problem with no control, that's at least not best practice. Yes. So if I understand, you're saying for an ODE that has a UVAR. Yes. So the control laws are only for ODEs that you've instantiated UVARs in. And the control law is a way of every time step dynamically changing what the UVAR is for integration.
But you couldn't.
Right. So if this is a two-body ballistic ODE, I don't believe you can append a control law to a ballistic because there's no UVAR to influence. We haven't allocated in the dynamics what this U variable actually represents. So it should error out and say, hey, you're trying to, on your first time step, you're trying to give me a U control, but I don't know what U is. You're now the improper size.
I guess, yeah, that's the key side. Where's the general side that they assume there's no implicit side.
Yes. Right. Yeah. Yeah. Your control law needs to handle the proper sizing. So let's take that two-body low thrust ODE that you wrote and let's do a test with, or let's do a practice with it now. So let's instantiate your ODE. And then once you've instantiated it, we want to make an integrator object, but let's do that integrator object with a control law. So the goal now, or the practice, is let's make a tangent control law. So a control law that always thrusts in the R hat direction of the RTN frame. So you'll need to make a vector function that is a tangent control law, and then instantiate that previous two-body with low thrust ODE that you wrote, instantiate that ODE, and then instantiate an integrator off of that ODE with this control, with this tangent direction control law. So we'll take some time to do this practice. Okay, let's keep moving on. So once you've got a control law instantiated, recall we already did this for the prograde burn. So all that changed in this case is we wrote the tangent law, which pulls the RTN frame and then applies the throttle in the tangent direction. So in this case, we are passing in throttle of 1.0 and instantiated the problem previously with a mu is equal to 1.0 and run it out. And you can see from this example that we plotted here that the prograde and the tangential burn are pretty similar to each other, although that wasn't really the, we're not really trying to quantify the change of those, but more just the practice of instantiating different control laws. So we, again, defined a function. You create an integrator object with your integration type, the default step size, and in this case, our new control law that you wrote, and pass in however many vector function arguments you need to pass in to these args. Then once it's integrated, you can integrate the trajectory using integrate dents out to a time final. Yeah.
Previous example.
Yes.
This one. It only did 3, 4, 5 in the integrator. Why were you using all?
So this specific example just reused the code from the RTN frame since we want tangent control. So you can absolutely just shorthand it and pass in a vector size 3 of your position to compute tangent. To compute R, or you can do and compute the pass in 6 and compute the RTN frame, or compute it dynamically. So prograde only needs size 3, right? Because it just pulls your velocity vector in points prograde. But tangent, you need to compute the tangent basis vector, which is technically R being crossed by, or crossed into, I guess I should say, the normal vector. So a tangent law needs position and velocity, versus prograde just needs velocity.
Okay. So I guess does your U back then need to be defined as 6.6
So your UVec will be in how we derived it here. The UVec is length 3, right? So when we wrote the equations of motion, UVec was size 3. So the whatever gets returned by your control law needs to return a vector function that's the same size as your controls. So in this case, our ODE is written to expect 3 U vector, size 3 U vector. So our tangent law or our control law needs to return a size 3 as well. So,
but then down there.
These are what get these. This is allocating what state vectors from our XTU get passed into this control law function. Yes, totally. Yeah, it takes a little bit of getting used to that syntax of that args term showing up again where, yeah, so the control law expects args size 6, and you can pass in any whatever size args your control law needs that you can pass from that XTU structure that we've got. So you can feed those in based on their proper indices of your ODE. Cool. So one more practical example. Again, reminder, the file that is on the meeting invite is broken into day 1 and day 2. It does have all the code examples from this. So if any of the code that we've shown on screen, it's on there to double check or cross check your code with. And then this is a practical example. It's a lot of code. So we're going to kind of talk through and walk through this example here. But all of the code for this example is part of the meeting invite. So you can pull it, run it on your machine. You can pick through it if there's any areas that don't make sense. But I'm going to walk through the code for this example. Please, in person and online, flag me if I'm saying something that doesn't make sense, that you aren't tracking what the example is doing. Yes. Yep. So for this practical example, we're going to do an actual orbit transfer initial guess generation using what we know so far. So this is kind of combining a lot of the stuff that we've covered in training so far for a kind of more real life example of there's some sun-centric body, green, that we are departing from. So we need to start on the green planet and we're flying out to some other arrival body, which is plotted here in red. So we've got a green departure and we want to go to or go towards the arrival body. So this is going to leverage a 2-body ODE, a ballistic 2-body ODE. It's going to leverage a 2-body low thrust ODE, which we've talked on, and use tangent law steering to find what's a good initial guess for this kind of transfer. So first things first. We obviously need to define some kinds of constants. We're again going to do this non-dimensional. So time max is this epic max. This is the max duration that we're going to allow propagation to go out to. So we set it to this arbitrarily large 100 size. We're going to later use event detection. So our integrators rarely will actually hit Tmax, but we're going to set Tmax, non-dimensional gravitational acceleration of 1, alpha, so our low thrust acceleration is 0.02. So if we need dimensional, how much is this thruster's alpha? We know that it is 0.02 over its gravitational accel. And we're going to set a throttle level for the initial guess. So we're going to say throttle it at half power, 0.5. So the first step of what we need to do is take the initial conditions of the departure and arrival bodies at some initial epoch time 0. So that's what this is. These are ballistic propagations, right? No, I don't know of any planets that have a low thrust engine appended to them changing it. So we're going to use the ballistic 2-body for this. So we recall that's 6 states in time. So we need a size 7 initial condition for the departure body and the arrival body. So we've got x, y, z, x dot, y dot, z dot, and time starting at 0. We then need to instantiate our ballistic 2-body model. So TB ODE is our 2-body model with our gravitational accel of 1. We create a ballistic integrator from that 2-body model. and we're just doing a default step size of 0.1. It's adaptive step. Then we also want to, we're going to use the spacecraft with a low thrust engine. So we need to instantiate a different ODE that has the two-body low thrust dynamics. So we instantiate that with, again, gravitational parameter mu, but also alpha. So how much acceleration can this low thrust engine supply? So we've now created and instantiated a low thrust ODE, and we're going to take an integrator from that. But an integrator, remember, now the initial conditions that we end up using for this low thrust, it's going to hold the control values to whatever the initial guess is, unless it's given a control law. So we're going to go ahead and create a low thrust integrator, give it that same default step size. Now we give it that tangent law steering, and then we needed to pass in, remember, a list of 0 to 6. So we're going to pass this is just another Pythonic way to write that list of 0 to 6, passed into that control law that we wrote in that previous example. So at this dotted line, what we have now is we have initial conditions of the planets that we're leaving and going to, and we have ODEs and integrators for the ballistic two-body problem and the two-body problem with a low thrust engine. So now we move into, let's go integrate the initial conditions of the bodies to generate just time history. Where are these planetary bodies going to be from time 0 to this maximum epoch time, Tmax? So because they're both ballistic, we take our ballistic two-body integrator. We're going to run integrate dense, so we get a control history from their initial conditions out to Tmax of 100. And we're going to return 20,000 data points, linearly spaced data points of these planets. So now we've got two time histories of the planets. But we're going to try and formulate a transfer between them. So let's load that time history, which right now is discretized time. Let's load those into interp table 1D. Remember those from the first slides. Load those into that so that we can have now a smooth piecewise fit that we can continually sample. So now we don't just have departing body trajectory, we have departing body table using the interp table, throwing that term in and allocating, or mentioning our time variable that we're doing the lookup from is index 6. So now we have interp tables of our departure body and our arrival body, and we have our ODEs and integrators. So now we still don't know when should we're going to start at this departing body, and we're going to have the same position and velocity as this starting body, and we're going to use a tangent law until we fly out. But we have no great way right now of knowing when should we leave, and if we leave, how long is it going to take us to get there, and where are we at when we get there? So we're going to use parallel integration. So essentially, we're going to do 4 years non-dimensionalized, so 2 pi to 8 pi non-dimensionalized, since our time unit is 1, means that's 2 pi is a rev, so 4 years worth of departure body revolutions here. So we're going to initialize a bunch of time zeros going from the times for 4 years of size 1000. So this is just NumPy doing a lin space. And then we're going to initialize a bunch of initial, for each of those time indexes that we're trying to depart from, we're going to construct an initial condition. So that initial condition, we can just set the states, so position and velocity, are equal to the departing body states at that time, right? Well, we have this nice convenient departure body table, so we can just pass the time 0 that we're constructing right now into that lookup table, and it will return the position and velocity of our departure body. So we can do that and append it to one large list of initial condition states. Our time finals, we just need that Tmax to be time final and make it the same sized length. So now we have a list of 4 years worth of initial conditions, 1000 sized list of initial conditions spaced within 4 years. And we have, there we go. And we now have a list of time finals. But that T final max is our maximum time. So we want to stop propagation at some point. We don't necessarily care to integrate out all of these 1,000 test points to all the way out to T max. So let's create a crossing event. And essentially what our target here is we want to integrate out using the tangent control law until we cross our distance from the sun is greater than the distance of the arrival body at that time from the sun. So we want to run all of these propagations out and stop integration once we've essentially reached distance from the sun that the arrival body is from the sun at that point in time. So we can define a crossing event vector function that we're passing in the target body table. We can get the position velocity or position time controls. We only really need the position time in this use case. So we get position of our body as a vector function and the time. The position of the target is that time lookup handed at, it's that time lookup table, that in target body table at our current time. We only need the position, so we're going to do head 3 because we don't, it's going to give us position velocity for the table lookup. Then we simply return the difference between the magnitude of our position minus the magnitude of the target body's position. So now we can run an integrate dense parallel on all 1,000 initial conditions, the 1,000 time finals, all of which are this arbitrary 100 term. And then we're passing in a list of events. This time it's the cross event 0. We don't really care if we're positive or negative crossing, just stop us when we reach that distance, and stop code of true. Then, of course, because we're running in parallel, we need number of threads. So we set it to 8 in this case, because that's a fairly safe thread count for most computers nowadays to run in parallel. So right here, Trage's events, we've run through this parallel integration. At this point, we now have 1,000 trajectories that fly out, starting at the departure body using a tangent law steering, flies out, and it propagates however long it needs until it is the same distance from the sun as the departure body is. But we've now got 1,000 potential initial conditions for our transfer. So the rest of this script is not even really an ASSET key. It's just using Python to sort through our list of 1,000, compute where's the arrival body at the final state of our trajectory time. And essentially, we're just going to sort that entire list based on the distance of our spacecraft integrated final state and the position of the planetary body. So that's all this section is just using Python to sort through our 1,000 integrated solutions and find the one that ends up closest to the planet. And if we run this and look, it's not an exact rendezvous. We don't perfectly reach the planetary body, but it's very close to a rendezvous where we have the departure body. We found the best solution starts when the departure body is up around in this area, and it integrates out with the tangent law and flies out, and then it hits its stop code and stops when it's greater distance from the sun than the arrival body. And the error between the two is actually very low. So just using the ASSET components that we've taught so far, you are very close to getting a low thrust transfer from body 1 to body 2. I realize that's the most complex buildup of all the systems we've been talking about for hours. Any questions on that? Okay. So again, you have the source code for that. If there was anything that felt fuzzy on that, definitely look through the code on that. And then tutorials online for ASSET's documentation. This should be a hyperlink. Good catch, Seth. Thank you. There should be a hyperlink to ASSET's documentation. that has other example problems being solved, so you can see the same methodology being done.